So last time we saw that even though this function x squared is curved and it's curved everywhere, we can come up with a function that describes the slope of this function everywhere. So this function has some measurable slope at every point on the function, and this function f prime of x equals 2x describes the slope of this function x squared at every point along the function. Notice this function gets steeper and steeper and steeper, and this value of slope goes up and up and up. Here we have a quadratic function, and the derivative is a linear function. So we want to take a look at how to apply this derivative definition, this is the definition of the derivative from last time, to actually find that function. So here's the definition written down. So let's suppose that the function we're considering, f of x, is x squared. So we want to plug that into the definition. So here's the definition, then f prime of x must be f of x plus h. So that's x plus h squared minus f of x, which we know is x squared, divided by h. And I forgot something very important here. It's that value in the limit that h approaches 0. So let's multiply this out. That's x plus h times x plus h. We remember we can FOIL that, so x plus h here times x plus h. I'm going to take the first times the first, and that'll give me x squared. The first times the last, so I have the outer here. That'll give me xh plus hx for the inner plus h squared for the last terms. Here's the inner and last. So I have the derivative here will be the limit as h goes to 0 of x squared plus hx plus xh, that's 2hx plus h squared all over h, and minus, don't forget this guy, minus x squared. So these two cancel. Simplifying, we see that we have the limit as h goes to 0 of 2hx over h. Let's actually split this into two fractions, plus h squared over h. So here, if h goes to 0 as fast in the numerator as it does in the denominator, even though this will be undefined when this is 0, if these approach 0 at the same rate, then the limit is still well defined. And because they approach at the same rate, this ratio is just 1, as you'd expect. So this is going to be 2x plus the limit as h goes to 0, I'm distributing this limit over the two terms, of h squared over h. Now I know h squared goes to 0 a lot faster than h does, so this thing actually goes to 0. So we get just 2x. And remember, that was what we found, that the derivative d by dx of the function x squared, let's use these for the derivative, is 2x. And we just showed that using the definition. Let's look at another example. Suppose that my function was f of x equals x cubed. So then the derivative will be f of x plus h, so that's x plus h, what? Cubed, minus x cubed, all divided by h. So this does not look like fun to multiply out. X plus h cubed. Well, I know that's x plus h times x plus h squared, and I already found x plus h squared. I remember from the last example that this was x plus h times x squared plus 2hx plus h squared. So now we can multiply each of these three terms by x. So I have x times x squared gives me x cubed. X times 2hx gives me a 2hx squared. X times h squared gives me an h squared x. And now I'm going to multiply the h times each of these three terms, so that gives me an hx squared plus h times 2hx, so that's plus 2h squared x, and then finally h times h squared is an h cubed. So I notice in this term I have one h and an x squared, and here I have an h and an x squared. I have 2 and 1 of those, so that's x squared plus 2 plus 1 is 3 hx squared, and these terms also are the same as each other because they have h squared but just one x. So I have 1 and 2 makes 3 of those, so that's a 3h squared x plus h cubed by itself there. So here, oh, what did I forget again? It's the limit as h goes to 0 of all this stuff. So that's the limit as h goes to 0 of this guy. Did you catch that? That should be a 3. To make that look nicer. So that is the limit of x cubed plus 3hx squared plus 3h squared x plus h cubed all over h as h goes to 0. And don't forget this guy minus x cubed. So again, I see that this guy cancels this guy. So this will be the limit as h goes to 0 of 3hx squared. Here I have an h and an h. Notice these terms have more h's, higher powers of h in the numerator, so they're going to go to 0 super fast. So they're going to go away, this term and this term. Their limit is 0. So I have a 3hx squared over h, and those h's go to 0 at the same rate, so this is just 3x squared times h over h is 1, and the limit of h over h as h goes to 0 is still 1, even though the quantity would be undefined when h goes to 0. So this tells us that the derivative with respect to x of x cubed is 3x squared.